we want to look at the points in which these functions are continuous. Let's start with the first function. We're given y equals 1 over x minus 2 minus 3x. Here, the only issue is dividing by 0. So we want to look at when is x minus 2 equal to 0. Clearly, that's when x is 2. So for any point that is not equal to 2, it's going to be continuous. So if you represent it with a number line, we want to pick all the points except 2. So we can write this as an interval notation. So it'll be from negative infinity to 2. Do not include 2, and then go from 2 to infinity. So that's the interval it's continuous in. Next example, given y equals 1 over x plus 2 squared plus 4. Here the worry is dividing by 0. So we want to look at when is x plus 2 squared equal to 0. If we square root both sides, we get x plus 2 is 0 and x equals negative 2. So it's going to be all points except negative 2. So we can write it like this. Okay. Next, we're given y equals x plus 1 over x squared minus 4x plus 3. Again, we're going to look at when is x squared minus 4x plus 3 equal to 0. So we can factor this out actually. We know that it's going to be x minus 3x minus 1, and that's going to give us x equals 1 and 3. So if we look at a number line, we want to include everything except 1 and 3, because that's going to give us, if we include 1 and 3, we're going to be dividing by 0. So we want to go from negative infinity to 1, from 1 to 3, and 3 to infinity. So that's the interval in which y is continuous. Okay. Next, if we have y equals x plus 3 over x squared minus 3x minus 10, we're going to be looking at when is x squared minus 3x minus 10 equal to 0. This one is factorable. We know x squared is x times x, and then we'll have negative 5 and 2, so that would just be negative 2 and 5. So it's going to be all values that are not equal to negative 2 and 5. So we can represent it in interval notation like this. Again, if we look at our number line, this is a great way to teach us or to show us the interval. Okay. All right, next we're going to be looking at an absolute value and a sine function. So we know with the absolute value, it's going to look like a v at x equals 1, and it's continuous everywhere. And sine of x is also continuous everywhere. So whenever you add two continuous functions, you're going to get a continuous function. So this is continuous everywhere. Okay. The next one involves another absolute value, but this time it's also going to be with a x squared term. So whenever you have rational functions like this one, you always want to check when the denominator is equal to 0. The x squared over 2 is a polynomial, and we know that polynomials are always continuous, so we're not going to worry about that. So we're going to have absolute value of x equal negative 1. Now the absolute value of x is always going to be greater than or equal to 0. it's never going to be negative. So there's no solution here. No matter what value you put in for x, it will never be -1. The absolute value of that will never be -1. So here, there is no point where it's going to give us any issues. So it's continuous everywhere. Okay. Now if we have y equals cosine x over x, cosine is continuous everywhere, so that's not an issue. But we want to check when the denominator is equal to 0. Clearly that's going to be when x is 0. So we want to include every point that is not 0. And that's going to be the interval in which it's continuous. Now what happens if we have cosine in the denominator? Well, first, x plus 2 is good. They'll never give us any issues in the numerator. So we'll look at when cosine is equal to 0. Okay, so here's a cool little way of doing it. If we look at the unit circle, cosine is 0 at pi over 2 and 3 pi over 2. And then you go back and forth. So you add 2 pi k and 2 pi k, where k is some integer. Now, a lot of people will say, okay, you can write it as pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k. But really, we can write this into one, we can represent it in just one way. So instead of having two of these, we can just say, well, I'm just moving back and forth over here. And the distance is always going to be pi. So I could just say pi over 2 plus pi k. Okay. So this is going to be where the denominator is going to be 0. So I want everything except pi over 2 plus pi k. So, okay, so that's the answer to that. Okay, next we're going to be looking at cosecant. We have y equals cosecant of 2x. Now cosecant, we can represent it as 1 over sine 2x. So here we're looking at when is sine 2x equal to 0, because we don't want the denominator to be 0. So let's eliminate all these points. Okay. In general, because this is a double angle identity, what I'm going to say is, okay, first let's look at sine. Let's say sine u, where u is 2x. Okay, so when is sine equal to 0? That's going to be at 0 and pi. Because u is 2x, we're gonna have to go another time around the circle. So the number here, the 2, tells us how many times we have to go around the circle. Okay, so we know it's going to be 0 and pi. Now we have to go another time around the circle. This will be 2 pi, and this will be 3 pi. Okay, so u is going to be 0, pi, 2 pi, and 3 pi. So u we said is 2x. So we're going to set that equal to 2x. And actually, we should say 4 pi as well. Wait, let's see. 0 pi. But I don't think it's going to matter at the end, though. So here we could just say 4 pi, because it's going to start repeating. So I think technically we don't need it, but it'll be fine. So x is 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, yeah, so this is one interval. So actually, I guess we do need it. Okay. Now this is going to repeat forever. So it's going to be like 0 plus 2 pi k, pi over 2 plus 2 pi k, etc. So all these plus 2 pi k. Now how do we represent this as a nice, concise way? So what we're going to do is notice that they're all pi over 2 units away from each other. Right? From 0 to pi over 2 is pi over 2. Pi over 2 to pi is pi over 2. Pi to 3 pi over 2 is pi over 2. And then 3 pi over 2 to 2 pi is pi over 2. So we can just say it's going to be any multiple of pi over 2 k, where k is an integer. So all these points in the form of pi over 2 k is where it's not going to be continuous. Not continuous for x equal to pi over 2k. So everywhere else, it's going to be continuous.